well, the awful task of being in between your whiskey tasting. I thank you very much for being here, and especially after a very, very inspiring morning and afternoon, it will be difficult for me. So, who I am the, let's say, digital advocacy person behind Euroheat and Power. We've heard a lot about digitalization and how we are planning to go ahead. I think I'm standing in the wrong place, perhaps in the middle, it's a little bit better. So, we are here tonight to award excellence in district heating and cooling from the young generation. So, if I could have my slide presentation, I'm not sure yeah, sorry. Okay, there we go. So the official title, as you can see, it's Young DHC Teaches Old Dogs New Tricks. So we really do hope that tonight you will learn something from our young generation. This is the DHC Plus Student Awards Ceremony for 2017. DHC Plus, I hope most of you know, it's the research and innovation branch of Euroheat and Power. And since 2012, we had a wonderful initiative to award the best students in the field. So we aim to support students all over the world in their research activities on district heating and cooling. And it's very, very many aspects. So from technological to environmental, social, and other aspects, such as legal aspects and so on. You already have there the line of honor from the previous awards. Just a very quick word on what the students get. Well, they get a research contribution of €1,000. Some of us may not think that that's a lot, but as I remember when I was a student, I believe that was very important, and it can very much help in their future. They can present at an international conference. This year, it is in front of you. And their research publication gets to be published in the International Euroheat and Power magazine. And every year we try to have a little extra, so what the winner of this edition, they will get a coaching session with David. So we hope that will be very, very useful for them. Very quickly, just to give you an idea that indeed we have a very big variety of students applying for the awards every year. It differs from year to year in terms of countries. You see a lot from Poland, Sweden, France, and so on. And we also have from very different backgrounds, from computer science to environmental studies, engineering, and of course, the good bunch from district heating and cooling. So I'm not going to waste any more time about this, but I would like to tell you one thing. The prizes are there, but it's not a given that they get the prizes tonight. They have to present in front of you, and you have to applaud. So hopefully, you're going to find them very, very, very interesting, because otherwise they go home empty-handed. So please bear with us. They will introduce their research, and after that we will take a short moment to award them. And I hope this is going to be an enjoyable experience from all types of generations in the room. So here we are. My honor to introduce to you the third prize winner, Carlo Winterscheid from Chalmers University of Technology. His theme for the paper that won him the award has to do with the integration of solar thermal systems in existing district heating systems. So, Carlo, please, the floor is yours. There you go.
Thank you. Yeah, my name is Carlo Winterscheid. I come from Germany, and I studied in Sweden before. And we all know the problem about climate change and energy consumption in our buildings, that it's an important factor we should change in order to meet climate goals. And for that, there are a lot of different solutions, and district heating is, I think, an amazing solution to meet those targets. I had the chance with my master thesis to work on a project that was to evaluate the possibilities of solar district heating. So I will first talk about the intentions of integrating solar heat in one example case, the methodology I used for that, the dimensioning for the solar collector field, the storage dimensioning, and I will show you some results of the simulation. The case that you see here, a little bit simplified, is in southern Germany, and it is one main network that supplies a subnetwork as well. Both network parts are supplied by a large combined heat and power plant that is based on carbon. And the challenge in this case was that the subnetwork needed 75 degrees Celsius, which is higher than the main network during summer. The idea then was to integrate a solar collector field with a storage and supply the summer month the subnetwork independent from the main network. Accordingly, there was not much input from the CHP plant, but we had the consumption data from the subnetwork. And finally, the operator of the system was interested not to have a backup boiler on the side, as the heat from the CHP plant is rather cheap. Here you see already the temperature level of the supply and the return for the subnetwork. And the two black bars limit the summer season that we would like to supply the subnetwork independent from the main network in order to have different temperature levels between the two networks. And this would not only allow us to operate the subnetwork independently, but it would also result in a better primary energy factor and reduced CO2 emissions from the network. And in the case of Germany, the primary energy factor is important from the building regulation in order to get some subsidies when buildings are created. As I said already, the independent operation of the subnetwork is beneficial for the whole network, and we will have more flexibility of the CHP operation, as it is sometimes, or it is mainly operated to supply electricity. The methodology that I applied is is a rather simple methodology. It uses the solar radiation and the heat demand of the network together with the temperatures. And then we said we use different solar shares, so we evaluated how the system would operate if we would have 5%, 10%, 15%, or 20% of solar share for the subnetwork. And additionally, we had a look how the system would operate if we would supply the equal amount of energy consumed in July, as it is the month with the lowest energy consumption, and produce this amount of energy from the solar collector field. Then this input data was used in a MATLAB algorithm that I wrote to calculate the solar field size and the storage size. And in the end, the results are then an overview how the system operates from hour to hour, the additional demand we would need from the main network, as we don't have a backup boiler on the side, and how the storage would operate and work. Here you can see already the consumption of the district heating network with the dark blue bars. Obviously in winter the consumption is higher than in summer. And in the different colors you see the solar fraction that was to be supplied by the solar collector field. And also you can see for July, the green bar is equally high as the dark blue one, which is there the supply for the overall energy we produce for the month from the collector field. And in this case, this is about 14% of solar fraction, which results in roughly 5 football fields of field area for the collectors. And that is about 0.1% of the subnetwork supply area. So compared to present 14% of the energy for this subnetwork, it's a rather small amount of field area we need to supply this energy. For the storage dimensioning, one requirement was to store only the surplus of a single day and not to have a seasonal storage. There is a lot of research at the moment on seasonal storages, which is quite interesting, but in this project it was said that we look only on intraday storages. So you can see in the graph the energy surplus that we have for each day of the year using the consumption data and the calculated solar energy production for each day. And the maximum point, which is, I think, 27 megawatt hours, defined then the dimension of the storage, which is about 730 cubic meters. And yeah, specifically it's 40 liters per square meter of collector area, which is rather small when you compare it to other values that you can get in other calculation tools. To show you some simulation results, in this graph you see only the summer season that is interesting for having the network parts independent. And in the first part you see in purple, or let's start with the yellow part, which is negative. That's the energy that goes into the storage. And in purple, above the zero line, there you see the energy that is taken out from the storage to supply the network. In the middle part, you can see the additional energy that is needed from the main network. So you can see you have a rather long period in summer where the solar heating system can supply the subnetwork rather independently. And I say rather independently because in this case, I already introduced the regular reheat of the storage, which was an option interesting to have the process of the CHP plant a little bit more predictable. So that means it's not optimized, but by seeing that the storage is close to be empty, the CHP plant and the main network can raise the temperatures in order to refill the storage on the side to have the system more predictable operating. And yeah, we see the load patterns of demand and supply, discharge and charging, the additional demand, and the periodic refill is down in blue. In the next graph, you see it a little bit more in detail for 4 days. So again, the yellow in the first graph, the yellow line shows the surplus of solar energy, whereas just above, we see in red the energy that goes directly from the solar heating plant to the subnetwork. And in the lowest graph, you see the state of charge of the storage, and the little blue peak below, which is at night, a little recharge of the storage. You can also see that at one point there is no decharge from the storage, and that's exactly the moment when we have the recharge from the main network. Interesting, you might also realize that even though we do a recharge with the main network, we don't fill up the storage to the level it had earlier on during the day. And that is because we have different temperatures. I calculated that we can go up in the storage up to 95 degrees Celsius, and the energy that comes from the main network would probably only have 75 to 80 degrees Celsius. So we have different temperatures, and therefore the energy amount in the storage cannot reach the same level. Then to come to the CO2 savings, we will achieve with the system or with the different systems. The 5 different points here are the different solar fractions. So in the left bottom we have 5% solar fraction, and in the top right we have 20% solar fraction. And the interesting point that you can see here is it has a slight curve. So after 15%, the direction changes slightly, and that is due to the saturation, so to say. So we have not enough consumption to empty our storage every day anymore, and therefore we cannot use all the solar energy. So if we have too large solar collector fields, we will not be able to consume all the energy, which is then wasted. Accordingly, we don't have the same increase in CO2 savings, and also we don't have the same efficient or cost-efficient network anymore. And that would reduce then basically the fossil fuel consumption of the combined heat and power plants. And if we just look at the lower part, we would have specific CO2 savings of 750 tons per 10,000 square meters. And in this case, I also used the CO2 emission factor of the CHP plant that was there on the site. So to sum it up, solar or integration of solar heat into sub-networks or district heating networks increases flexibility for operation of different, for example, the heating plants, the other heating plants existing, but also in this case specifically for the temperature levels in the two networks. That results in partly independence in the sub-network. In some phases, it's really that it is not needed to have any reheat of the storage because the storage is filled up to a sufficient level during the day of the solar heat. Then for the dimensioning process, it's really an offset between the collector field and the storage dimension and the independence of the main network or the subnetwork from the main network, obviously. And the more one invests into a system, the larger it can be. I mean, that's quite clear, I guess. And it's also quite important that we can reduce the primary energy factor, as it is in German important in the building regulations. And with that, as the primary energy factor depends on the CO2 emissions, we have also a reduction in CO2 emissions. And in general, during this simulation, which is kind of a tool or a calculation between a very, very simple one and a very, very advanced one. So it helps to do a pre-evaluation if it is worth considering solar heat in a network or not really. And it turned out to be quite useful to use hourly consumption data and temperature data of the subnetwork in this case, as you already get some quite reasonable data as a result. And solar heat in general, or solar district heating, should, from my point of view, considered for much more projects. In Germany, there are some projects which have applied solar heating only in refurbished areas with low temperatures. But from my point of view, after this project that I was able to do, it seems like it's also quite interesting for if you just want to have standard or average temperatures in the district heating network, you still get a quite reasonable amount of energy out of the collectors. And by the example of Denmark, with a lot of large solar district heating systems, I think that speaks to some extent for itself. And with this, I want to thank you for your attention and would ask you to come to me later if you have any questions or to talk about details when it comes to the calculation, or if you're interested to develop the code that I wrote into a tool that can be used like for everyone. I'm happy to share it. Thank you.
Okay. I believe you have earned your prize, so I will do the honors right here. Thank you very much for a most interesting presentation. Congratulations.
Thank you very much.
There you go.
Thank you.
Okay. Yeah, you can have it. It's all yours. Okay, you can look at our photographers. Okay, there we go. Have I mentioned that the actual jury every year has a very, very difficult task, because the level of the presentations it's very, very, very high. So, without further ado, I am going to introduce you to our second prize winner, Michal Leszko, from the Warsaw University of Technology. His paper relates to the modeling of combined heat and power plants for optimal planning of their production. Michal?
Good evening, ladies and gentlemen. Can you hear me? Yeah. I will talk about modeling of combined heat and power plants for optimal planning of their production. And the research I will present was done as a part of cooperation between my university, Warsaw University of Technology, and Veolia Energia Warszawa company in which I work. Plan of my presentation. First, I will give you a short introduction. Then I will talk about optimization of CHP plant production with energy storage. I will talk about modeling of CHP plants, which is necessary for such optimization. I will present a short case study, and of course, I will summarize. Traditional approach to district heating could be summed up in such a way that historically, from the point of view of district heating company and CHP plant, the electricity price was rather stable. The heat price was stable if it existed at all, because in some countries there was no price. And the fuel price was also rather stable. The appliances used in the district heating network were manual, both in terms of valves and in terms of measuring devices. As a result, it turned out that most companies found it optimized to follow the load curve, which is a simple function of outdoor temperature, and to follow a regulation table in terms of supply temperature. So for specified outdoor temperature, we had specified supply temperature. But now, this is no longer the case, because as we all know, the situation has dramatically changed. First of all, the electricity price is highly variable, and the combined heat and power plants are needed for balancing the electric grid. The fuel mix has become more diverse. At the CHP plants, we have gas, biomass, waste, coal. The fuel prices also became dynamic, especially gas price. The flue gas emissions are restricted in more and more complicated ways. So the task of planning the production has become much more complex. At the same time, the technology has progressed. So we have now widespread telemetry, we have access to thousands of measurements from all the network, and we have remote control of valves and pumping stations in the network, which gives us new possibilities to optimize. So the conclusion could be that district heating systems, and especially the ones supplied with CHP plants, need to adapt to changes in the market, and can adapt to changes in the market because there are new technical possibilities. And especially the key is flexibility, because we have environment, we have smart grid with variable electricity price, we have smart district heating, which means for me telemetry and remote control, we have modern fuel market, and we have CHP plants in between. And what is the answer of CHP plants? Of course, it's energy storage. As we all know, it's much easier to store heat than to store electricity. So it pays to store heat for the purpose of CHP production. And we have three ways of storing the heat. We can use the thermal inertia of buildings, of hot water reservoirs, and of inertia, and we can use the thermal inertia of the network itself. Now, how does it affect our optimization task? Historically, you could say that optimization of production plan for CHP plant meant that we have to find good distribution of the load between our production units, which means tens of variables. For every production unit, we had to specify the electric power, which I will denote with P, and heating power, which I will denote with Q. We also had to find heating powers for peak boilers. And we could do it hour by hour, because if we didn't use storage, or we didn't explicitly use storage, then for every hour we just had to meet the load demand. Now, if we add storage, It might seem that we are adding 5 to 10 variables, for example, heating power of charging or discharging the heat storage tank. But in fact, what we are doing, we are multiplying the number of variables to optimize, because we can no longer optimize hour by hour. We must optimize full time series. So, for example, time horizon of 72 hours. So that means we have to optimize thousands of variables, and there is not much time for it, because the time between receiving the last forecast of weather or electricity and sending the production plan can be 5 to 30 minutes. So we need simple and fast models for simulation of CHP plant behavior in order to be able to make such an optimization. And the simplest and fastest models are, of course, linear models. So I will present two approaches to modeling CHP units of building linear models. I will talk about back pressure turbines. So typically, back pressure turbines is understood as a turbine which produces electric power proportionally to heating power. But in large CHP plants, the turbines always have steam extractions, and they usually also have the possibility of cooling district heating water, which is called pseudo-condensation. So in fact, these turbines have at least 2 degrees of freedom. On the graph, this represents using the steam extraction. It can be fresh steam or intermediate pressure steam. And this, our arrow, represents pseudo-condensation. So how can we model such a turbine? The first approach is equation approach. So we basically build an equation, linear, as I said, which will tell us that the electric power will be a linear function of heating power streams. Heating power at the exhaust of the turbine, at the steam extraction, and the condenser or cooler. And it can be also linearly dependent on the temperature of supply, temperature of return, and boiler feed water. Now, if we have such an equation, and we write it ourselves, we need to add constraints, and it's not always easy to add the constraints, because the constraints include maximum power of the boiler, maximum power of the steam extraction, minimum power of the turbine, minimum power of the boiler, but it can be more. It's just an example. And we need to write these equations ourselves. We also need an equation which will tell us how much fuel we consume, so how much energy in fuel we consume. Of course, we can write an equation summing the useful energy streams and dividing into it by efficiency of the boiler. Now, if we assume that the efficiencies are stable, or that the changes of efficiency can be attributed to temperature of supply, return, and boiler feed water, we can rewrite this equation in the same form as the equation for power. In this equation, there is no power, because if the electric power is already a linear combination of these streams, we can include it here by changing the coefficients. So we have two simple equations, and we need to specify constraints. Now, second approach is a topology approach. It means that instead of writing the equations ourselves, we build a model by connecting simple elements, and the equations are specified by the connections between the elements and by the characteristics of the elements, which are given with a very simple set of parameters. For example, how do we model a turbine? Turbine will be an element which splits the energy of incoming steam into electric power and energy in the outgoing steam. And what is interesting here, even if this equation is linear, because it should be linear for the optimizer, it doesn't mean that the PQ ratio is stable. It's not even linear. As long as this B coefficient is non-zero, our PQ ratio is variable, so we can get more accuracy. Boilers can be modeled exactly in the same way. So linear function telling us how much energy in steam will go out depending on energy in the fuel. And again, the efficiency doesn't have to be stable or linear. In fact, it's non-linear. Someone will say, okay, it's not linear, but it's monotonic. If we want it to have a maximum below the maximum power, we can divide the load interval into two load intervals. In both load intervals, we have linear function, but different linear functions. And then we get the maximum of efficiency where we want it. And the efficiency curve resembles the theoretical efficiency curve. So the advantage of topology approach is that it's a very comprehensive method. So there is a low risk of errors, and if there are errors, they are easy to find. It's highly replicable, it's clear, but we don't see explicitly the set of equations. So there can be some unnecessary equations implied by connections of the elements, and not all rules and constraints can be modeled in this way. On the other hand, equation approach gives us full control over the equations. So there are no unnecessary equations unless we add them. And there is possibility to model every kind of complicated constraints. But the model has to be created manually, and therefore there is a high risk of errors. And it's low replicability, because if we didn't create this model, this set of equations, it will be hard to correct it, to change it, and to replicate it. It's possible to use a mixed approach, which means topology approach with special equations when necessary. Now I will quickly show a case study. Case study was done on historical data from one production unit in Poland, hourly data from 1 year. We see 3 graphs: heating power from the turbine versus gross electric power, total heating power versus gross electric power, and total heating power versus energy consumption in fuel. As you see, the measurements are never very accurate. There are some changes of efficiency. And this block was used not only as a back pressure turbine, but it was used also in pseudo-condensation. You see here electric power with low heating power. And it was used a lot with steam extractions, even fresh steam extractions. You see very high total heating power at low electric power. So I modeled this block with 3 approaches. Equation approach, you see in the red the points according to the model. So equation approach gave the mean absolute percentage error of about 3.8% for electric power and 4.04% for energy in fuel. Topology approach with 1 efficiency interval gave higher mean absolute percentage error, of course, 5% with electric power and 4.67 for energy in fuel. But as you can see, this very simple model allows to see the trends and to model this unit. Maybe precisely enough for optimization of planning. If we use 2 efficiency intervals in topology approach, it gives us slightly lower errors, but still higher than in case of equation approach. So to sum up, optimization of CHP plant production with energy storage requires simple, and by simple I mean preferably linear models of production units. I showed 2 main approaches to this kind of modeling. One of them is equation approach, which gives us potentially higher accuracy and better control of the equations, but we need to create the equations manually. And topology approach, which is used by commercial companies, by commercial software, is more replicable, it's clear, it's easier to understand, but it may contain unnecessary equations, and we don't have full control of the equations. And a mixed approach, which means topology approach with additional equations, can be used to combine the advantages of both. but we must be careful not to add too many special equations, because then we combine the disadvantages of both. Here is the list of references. Thank you very much for your attention.
I think he deserves his prize, yeah? Thank you very much. Michal? Thank you. Congratulations. Yeah, sorry.
Thank you.
Thank you very much. I think our photographers are there. Okay, thank you. Please take your seat. In moments like this, I wish I paid more attention in physics class. But I believe we all have our roles, so. And my role at the moment is to introduce you to our big winner, which is Gerald Schweiger from the Institute for Sustainable Technology of the Technical University of Graz. And his research focused on the framework for dynamic optimization and stimulation of district heating systems. So, please, get up. Go ahead, if you want. Yeah. Serious presentation.
1, 2. Can you hear me? Yes. Okay, thank you very much for the nice introduction. Today I will talk about the framework for dynamic optimization and simulation of district heating systems. So let me start with the motivation. Sorry. Okay. One may ask if you see or hear the topic, oh, another novel framework for simulation and optimization. I think there are hundreds of studies popping around, a lot of publications. Everyone points in a certain direction, so there are ideas, there are concepts. And for me as a reader, sometimes I even smell this lobbyism out of this direction. So you see, we need storage, we need a peak shaping, we need whatever. So I was really glad to work in a team, what's a joint effort of industry, applied research, and university, where there's no particular interest. So we are not interested in a certain system solution. We don't care if it's heat pumps or storage or whatever. So what we want to do is we want to provide a framework that allows a detailed, fully dynamic thermohydraulic analysis of different system solutions. And this framework, we want to provide a maximum flexibility. That means we want to be modular, extensible, adaptable, and it should be usable for industry and research. So to sum it up, we don't care about what the system, how the system may look like. We want to provide a framework to compare, to fair compare different system solutions. So our scope is urban energy systems, and we know the ideas, we know the concepts, and the first stage of our research was to translate these ideas and concepts into numerical requirements for dynamic optimization and simulation. So, for instance, smart energy systems, and there will probably be an integration of different domains, they call for so-called multi-domain languages. There will be probably renewable and industrial heat surplus, we don't know. If there will be, that require tools that can handle highly dynamic simulations, so this will increase the dynamics. The same for active demand response that calls for sophisticated control, and there will be probably multiple supply temperature levels. So when we talk about dynamic simulations, for those of you who are not familiar with applied math, dynamic simulation can be hard to solve problem for sure, but when we talk about dynamic optimization, this is on a completely different level. So dynamic optimization, and now I mean really fully dynamic as the system is, for district heating involves both discrete and continuous decision variables. Discrete variables are if a unit is on or off. Continuous is what's the certain mass flow, what's the temperature, what's the pressure. We involves, unfortunately, transport delays. So that's easier to model power systems. Here we have huge transport delays, could be 2 or 3 hours from the main production unit to a certain consumer. And everything is highly nonlinear and dynamic behavior. So this problem is called a mixed integer optimal control problem. When you talk to control engineers, when you talk to math guys, they call it mixed integer dynamic optimization problem. Unfortunately, there's no robust and scalable method for real-time application, and here the highlight is real-time application. So there are some approaches available, mainly some generic or heuristic optimization methods, but they are not available for real-time applications. Another drawback is that so there are sophisticated numerical methods, especially for the continuous problems, but in most cases they are implemented on a really low level, means in C++ or Fortran or whatever, so they are not inappropriate for engineering applications. Why do we use Modelica? Modelica is a modeling language. For those who don't know, I just want to give you a short overview why we use Modelica. So we try to combine the advantages of equation-based modeling. And when I talk about equation-based modeling, it's not the same that the previous speaker talked. So generally, there are two ways of modeling systems. One is equation-based modeling. The other one is what we call causal modeling. There are pros and cons for both methods, but when we talk about equation-based modeling, it's especially good for me as a modeler. It's bad for the computer. The other one, the causal modeling language, it's really close to the solution algorithm, but for me as a modeler, it's really hard to somehow change my system that it fits to this. So equation-based modeling, good for us, bad for the computer. And Modelica is a multi-domain modeling language, which means we can model not just heat, not just power, not just whatever, biomechanics. We can model whatever we can describe through differential algebraic equations. The advantages of out-of-the-box modeling, when I talk about out-of-the-box modeling, I mean the following. This is a Modelica environment, and out-of-the-box means I just want to use models that we implemented and just drag them in, connect them, as they are in the real world. So that's the main advantage compared to really low-level approaches where you always have to go on text level and you have to type your equations. Here, we provide a library that's fully available. For sure, Modelica offers the possibility to dig into the code, to change the code, but this is an advantage. And we want to provide these sophisticated numerical methods for this framework. So what are the main contributions we developed? And when I talk about we, I mean, I worked in Sweden with the company Modelon, which are the main developers of Modelica. I worked together with some professors at LTH Lund, at TU Graz, so it's not just me. But we developed a framework for creating manipulating networks, as well as translate it into executable code. So I will discuss the framework in detail. Then we developed a library for complete out-of-the-box models, for all kinds of models, for dynamic simulation and optimization. Some of the models we can use for simulation and optimization, but there are certain restrictions to optimization. For instance, they have to be twice continuous differentiable and stuff like this. So we cannot use all models for simulation and optimization. And more from the theoretical side, we developed a method for decomposing this, what I said there, this is called mixed integer nonlinear optimal control problem. And we implemented a method that decomposes the system, separating the discrete part from the continuous part. I will discuss it later. So what's the core or the heart of our framework is so-called a unified network representation. So any on-grid energy system, like a power system, a gas system, a water system, generally consists of nodes and edges. A node could be a consumer, a prosumer, a generation unit, a storage, whatever. And a node, depending on the domain, could be a distribution line, could be a gas pipe or a district heating pipe. So a straightforward approach, what we thought is, in general, we get this network plan, GIS or CAD, whatever. So we implemented an interface to translate this CAD or GIS into a Python framework that's implemented in Python Network X module, which is a very powerful module to describe and analyze graphs. This is then translated into the simulation tool code, in our case Modelica, but it would be also possible to translate it to MATLAB Simulink or to C or to Java or whatever you want. Next thing is the network aggregation. So this may be an original network, a very simple one, but we worked with, I don't know, 400, 4,000 consumer. And when we talk about continuous optimization, again, very hard to solve problem. So we have to somehow reduce the complexity of the network, and this is called so-called aggregation methods. They are well known, so this is not something new, but we implemented this in Python Network X. This is based on early 2000. We know from papers and from studies that we preserve the name dynamics and the main characteristics of the network when we simplify the topology. But we need to do this in order to optimize it. The next thing is what I said before, the novel method was to decompose this entire optimization problem into a discrete problem and a continuous. So now we're talking about the mixed integer means the discrete problem. So again, an example, maybe this is a planned city district in my hometown in Graz. There are probably maybe 3 production units, and the whole idea of a discrete problem is to, given any costs, so we want to provide maximum flexibility. Any costs, maintenance, startup, we have restriction, ramp down, shut down, whatever you can imagine. It's implemented in Python Bioma, which is extremely beautiful because it's an algebraic modeling language. It means you can describe your problem as you would do it on a piece of paper in math. So I just write minimum, whatever, maintenance cost, maximum, any profit, whatever you want. This is called a mixed integer quadratically constrained problem, so we are not linear, we are quadratically constrained, but it's very robust. We can solve huge problems in a couple of seconds. The main result of this step is the status for each production unit. So as you can see here, so we don't care about what's the actual load, what's temperature, what's mass flow. This is done in the next step in the continuous problem. Here we say this is just the status of the unit. So then we come to the, let's say, the hard and the real interesting thing when we talk about numeric and math. This is how do we solve the continuous problem. As I said before, so the status of each unit is given. We know when is production unit A, B, C, when it's on or off. So this is set, and this leads to a, sorry, this is the only math slide, I promise. So this leads to a continuous dynamic optimization problem. A very generic form. What does a continuous optimization problem have? It has a cost function. What's here in the generic form could be anything you want. Again, we could talk about costs, we talk about temperatures, mass flows, ecological parameters, whatever we want. In the most simple way, in the use case I show you later, we just minimize supply temperature. The very beautiful of these equation-based modeling languages is that they are really well suited for dynamic optimization. So we model the entire system and we throw it into the optimization problem. And these constraints have to hold at every iteration. We have additional path and parent constraints. Let me show you how this looks like in Modelica. So again, on the left side, we have the model out of the box. This is how you can model. Any engineer can do it. We model, we have probably new system solutions, whatever. We formulate an objective function. Here, in that case, minimum supply temperature. We have some additional constraints that may be just artificial here. The mass flow at the production unit has to be less than 15 kilograms per second, and the minimum differential pressure in the system is always greater or equal to 0.5 bar. Okay, a little math, this leads to an infinite dimensional dynamic optimization problem. It's not possible to solve it analytically, so we have to use methods that are called direct methods to somehow transform this system. What do we do in our case? We use a method, that's so-called the collocation method, to get a finite problem. That means when I have my entire dynamic optimization problem, normally I go through the system one by one. So what we do, we use a Runge-Kutta method. We state the entire system at once, and then we can solve it with a nonlinear programming solver. An ordinary nonlinear programming solver, they are really known methods. This leads to especially sparse problems, so we have very well-known problems, how we solve this. So now I want to discuss two use cases. We developed the use cases not based on real applications, so we're not really interested, is this real? What we wanted to do, we wanted to stress the numerics. So this is a real district heating network located in Austria. 2017, there's just one production unit. We adapted it to, they are planning the top unit and the solar unit, as well as to reduce the supply temperature. We thought probably they will integrate a power-to-heat unit, and they will probably 2040, they will integrate so-called prosumers, whatever. There was no idea for 2015. So that's all what we knew. We wanted to stress this framework regarding numerics, and now I want to show you some results. So the most important thing is, it doesn't matter if we're going to 2017 or 2040. For the framework, there's no difference. We can handle all these requirements. That's probably not that interesting for you. For us, it was really a huge success. So we can model the so-called temperature wave propagation in a numeric, very sound way. So this is a step function in orange at the producer, and you see this is really propagated without changing the profile in the entire system. So this is very important for the future when we will have to model such system. There could be a case where we have a power-to-heat unit that has to ramp up very fast, and then ordinary tools, quasi-stationary tools, they cannot model this. We can do it in a very nice way, I would say. Another thing, from a numerical point of view, it's not that easy to handle zero and reverse flow states for mass flow, so we had to adapt all the models for this kind of reverse and zero flow states. So in that case, we implemented this top unit, and where the circle, and you see the orange graph, this is the mass flow in a circle, somewhere in a pipe, doesn't matter where it is, but you see when the top unit is on, the mass flow direction change without introducing any numerical noise. So, and even the computation time doesn't change. So you can model these future systems without losing computation time. Another thing, this is about a heat unit, very simple implementation. We said when the base unit is above a certain level, we have this power to heat unit that heats up the return. just to demonstrate, again, however, even if that's not realistic, we can do it without problems. Last thing, a case for dynamic optimization. This is again the planned city district in Austria. So we said here, okay, we want to have a very simple optimization problem. We want to minimize the supply temperature given a certain value before. So we prioritize the supply temperature, and then we say the pressure at the production unit. This may somehow be also realistic, because in a real network you want to minimize the supply temperature and the pressure. Given the entire system dynamics, so we have to model the system in Modelica, and then we had some additional constraints. And here, the really, really nice results. So as far as I know, we are the first that can integrate this temperature wave propagation, what we call mass flow dependent transport delay, also in optimization. So we can do with almost the same accuracy what we do for simulation, we can do for optimization. Another thing is, and that's a very, very huge benefit compared to all the approaches, we can put constraints on physically relevant variables into optimization. So we don't have like simplified models, we have the real models. We say, okay, here in that case, the differential pressure has to be higher than 0.5 bar. And here you see, this is the differential pressure customer O, which is the furthest away. It's not going below. So we have these physical constraints in the optimization formulation, and we have this entire model. So let me conclude. For simulation, the framework is suitable. It's definitely suitable for all kinds of requirements that we know so far. And we can do everything fully dynamic, thermohydraulic. For optimization, we're really proud to develop this robust method to decompose the mixed integer problem. That's more a theoretical problem, not that interesting for application, but that's what's really cool. Very important for us, the solution time is sufficient low for real-time application. And especially when we talk about MPC, model predictive control, that means we're close to using our method to implement it on a real-world problem because the solution time is sufficient low. We can handle mass flow dependent transport delays, and very important, it is possible to include these constraints on physically relevant variables like temperatures and mass flow. But compared to all other approaches, we have really the model, so we have the physics, we have the math behind the equations, and that's in the optimization formulation. And this improves the reliability of the results significantly. Thank you.
Okay. Well, Gerald, I think you have earned your prize as well. Thank you very much. I don't know if that was 150 words per minute, but that was a very comprehensive presentation, and your research equally. So I want to congratulate you.
Thank you very much.
There you go.
Thank you.
Okay, welcome for just a couple of. Okay, please.
Thank you very much.
Unfortunately, we don't really have that much time for questions at the moment. But one of the real values that we probably didn't put on our slide is that we offer our student award winners the possibility to network with you, to be able to explain a little bit further. So if you do have any questions for them, or you want to congratulate them, or you want to know them better, please do so during our evening event, and I'm sure they will be able to help. I do have, there we go. So we handled the questions. And a very last word about DHC Plus and our initiatives in education and training. We do want to remind you that our other big initiative is the summer school. 2 of our students have already been to this wonderful event, I believe 2 years ago. So you see that things go connected even further, and we do want to invite you to spread the word about the summer school in your networks, and of course, if possible, to support our initiatives. And we thank you for your support so far. So this concludes our evening and our award ceremony. I do have one housekeeping note to tell you. Those of you who have registered and have a voucher for the evening event tonight, we are leaving from the entrance here at the conference center at 18:50. Yeah, so that is 10 to 7, and there will be a couple of buses that will take us there. So thank you very much, and I would like to invite our winners a little bit more on the stage that we can take some group photos. Okay, thank you again, guys.